cross-validation is used everywhere for many different purposes. In many situations when we are like dealing with hyperparameter tuning or selecting a model, we use cross-validation. So that's why the topic of today's session is very, very important. So any questions before we start? No? All right, so you have access to this Jupyter file. So I'm going to first go over cross-validation for cross-validation for classification. So you may remember the iris data set, which is about 3 types of irises. We have setosa, versicolor, and virginica. They are class 0, 1, and 2, and the features we have are measurements of the flower. So we have sepal width, sepal length, petal width. And the idea here is that we want to use a KNN, a K nearest neighbor classifier, to predict, what a certain, flower with certain measurements belongs to based on these 3 classes. So we can load the iris data set directly from scikit-learn. There are a couple of simple questions that I'm sure you know how to answer. For example, shape of the data is 150 by 4. This means 150 rows and 4 columns. Then the type of data is NumPy float, because these are just floating point numbers. Number of samples is the number of rows in the data, 150, and 4 is number of columns or number of features. So raise your hand if you have any questions. Otherwise, I'm going to just go very fast for these basic parts. I'm going to just put the targets in target data and names in target names. So again, a couple of easy questions on what the target data looks like. So it has 0, 1, and 2. And these represent setosa, versicolor, and virginica. So the type of these names are string, but type of these, class labels are integer. Then, like another question, how many samples are of type setosa? So to find the answer to this, we know that setosa is where target equals 0, where the response equals 0. So we can just look for this. We can take the sum of the number of records where target data equals 0. And here I'm using a formatted string in Python. And what this does is that, it calculates this, and it has this % operator which puts the result of this in the sentence I'm writing. So if this is confusing, don't worry about it. We don't have to use this. So a different way of doing the same thing is just, print for 2 arguments, you print a string, and then you print a number, right? So the first one is kind of a more professional way of printing an output. So you can see that this one says 50 samples of type setosa, which is pretty much same as this, right? Any questions? All right, so now I'm going to just plot the data with colors representing the types of these irises. And I guess a bit better. So, and this is the feature space, because X and Y axis are both representing some features, and the colors represent the classes, right? So you can see we have these 3 types of irises. So what do you think is special about this plot? What is interesting about it? One. Exactly. You can see that the blue data points are separated from the rest. And what this means is that if we want to make distinction between setosa and versicolor or setosa and virginica, the task is not that challenging. The more formal way of saying the same thing is that the binary classification task of separating setosa from versicolor is a linearly separable task. This is because you can imagine drawing a line here, just follow my cursor, and separating blue from orange or separating blue from green. As the separation only needs a line, it's easy to do that because you can just use LDA, linear discriminant analysis, and find that line and separate them perfectly. You can also use logistic regression. Actually, logistic regression for linearly separable tasks is not the ideal choice, but that will also give you some relatively good performance. So this is because logistic regression is developed in medical sciences where nothing is easy, you know. Predicting whether a patient survives or not is just, it's from human body, which is so complex, and there are many factors, right? That's why logistic regression works for complicated tasks, but actually kind of disappoints us sometimes for easy tasks like here. But there are, you know, different methods can do well for separating setosa from any of the other one. But if you want to separate versicolor from virginica, that task is a non-linearly separable task, which means that you can separate orange from green if you manage to find a boundary that looks like this, looks like this. So just imagine, you know, the mathematical formula representing this weird shape, you know, how ugly it is. That's how difficult the task is. So if you can somehow, you know, find the function that defines this weird kind of path that I just followed, that's how you can classify between versicolor and virginica. All right, so here we're going to use a KNN based on one neighbor, right? So that's a nearest neighbor classifier. And if you remember from last week, a nearest neighbor classifier is likely to overfit to the data. So I'm going to just put the features as X, target data as Y, and this is KNN with N being equal to K being equal to 1. So I'm fitting it to the data. It's fit, the classifier is fit, which means that if we just provide some measurements on a flower, it's going to give us a prediction. For example, if we say, what type of flower has, you know, 3 centimeters. So we have a flower, it's 3 centimeters for petal length, 4 centimeters for petal width, 5 for sepal length, 2 for sepal width. What type it is more likely to belong to, right? We can ask this question from a classifier after it is fit to the data. So then when we provide to the classifier, it is one point in the 4-dimensional space. That classifier for making a prediction is going to look at the neighbors of this and see what other flowers have these sort of numbers. And then based on those neighbors, actually based on the one nearest neighbor to that, it makes a classification. So we run this and it says the prediction is class 2 or virginica. This must be because there is some virginica in the data set which matches with these numbers or which is very close to these numbers. Any questions? If you don't ask me questions, I will ask you questions. Yeah. Yeah, this is because here we're providing NumPy array, so we can see if we just put this, I guess it's going to also give us some likelihood or something. Let's see. Okay, it's going to return an array of a number, right? So just the format of the output is a NumPy array, not an integer. But when you want to access the number inside an array, you want the index of that. So this way, I just converted the output so that it becomes something that I can use in here as an integer. All right, so now my question for you. What would be the accuracy of this classifier on the training data? 100%. So this is one way of getting accuracy. I'm just checking for how many data points in the training data the target data matches with, this is the response, matches with the prediction based on those features, right? And you can see that the accuracy is 100%. So, but there's a customized function also in scikit-learn that allows us to do this. And if we run this, this also gives us 100%. So, any questions? So what does this mean when training accuracy is 100%? We are overfitting to the data. So with cross-validation, we can decide between different KNN classifiers with different values of K to see how many neighbors we should use to not overfit to the data. And at the same time, not being, underfit. That's the other extreme. It's not just a matter of changing K to a large value, because maybe if we go with a value too large, it would be underfit. So, all right, so for cross-validation, this is how cross-validation works. So it's based on the idea of being more efficient in using the accessible data. So let me change to the document camera. All right, so you may remember the three-way split from first week of the course. So with three-way split, the first thing we did was separating some holdout data or test data and then calling the rest accessible data. And then this accessible data, we then separated it to validation and training. But that was sort of wasteful because this is accessible and it doesn't really make sense to not use it, use only a part of it for training, right? Especially because in many situations we deal with cases where n is small. So even when we separate another part of this and call it validation, that's not really a good idea. But at the same time, we cannot train a model on a data point and also evaluate it on the same data point, because that would be kind of cheating. The other issue is that if the performance is good, we don't know the model has the capability to generalize, or the model is just memorizing the data. That's the issue. So that's why we have this idea of cross-validation, which is a smart way of dealing with sort of challenge. So cross-validation allows us to use this accessible data both for training and validation, such that for every model that we train, there is no overlap between validation and training, so that our evaluation is relevant and meaningful. At the same time, it allows us to kind of reuse this accessible data for different purposes. So let me explain how it works. So this part is a bit complicated. I really need your full attention. So let's say that we have this accessible data in black. This is the same accessible data. I just split it into three parts, and I called them three folds. Fold 1, fold 2, and fold 3. Then with these three folds, I'm going to actually start a three-step process. Each step of that process is called a split. So we have split 1, split 2, and split 3. All right, so in split 1, I'm going to use fold 2 and fold 3 for validation, for training, and fold 1 for validation. right? If I do this, there is no overlap, right? So this gives me a classifier, and that classifier can be evaluated on fold 1, and it's going to have some MSE. For example, the MSE I get from that, I call it MSE1. MSE sub 1, right? And this is only the first step of the process. In the next step, I'm going to change how I'm using the folds. So in split 2, I'm using fold 1 and fold 3 for training and fold 2 for validation. Then I evaluate this classifier, which is a different classifier from the previous step. This is now a new classifier. I evaluate it on this validation set, which is fold 2, and its performance is MSE2. Then in the last step of this 3-step process, I use F1 and F2 as training and F3 as validation. So the MSE I get from here, I call it MSE3. So now I have 3 MSEs. There are 3 numbers. I can take their average and their standard deviation. So the average, I call it mean of MSE1, MSE2, MSE3. I take the mean of these. I call it mean MSE cross-validated. The same 3 numbers, I can take the standard deviation. So I take the standard deviation. This is standard deviation, nothing else. MSE1, MSE2, MSE3. I call it standard deviation of MSE cross-validated. And all of these things that I did was only based on k being equal to 1. That's why everything has a superscript of 1 in green. Then I repeat everything with k being equal to 2, and I get in MSE cross-validated superscript 2 and standard deviation MSE cross-validated superscript 2. So in K and N, K can be 1 or 2 or 3 or 4 all the way to N, right? So we need to continue this for other values. That's why I'm going to also try K being equal to 3, 4, all the way. Then from this process, all right, so any questions so far? Because this was already quite a lot. No, we will see. We usually go with 10 or 5. Here I just went with 3 because I was lazy writing more things on this piece of paper. So usually 5 or 10. K is the hyperparameter for K and N. So K and N is the idea of looking at the neighbors to classify. So we can look at 1 neighbor or 2 neighbors or 3 neighbors. So therefore K is a parameter. K is a parameter for KNN classifier which impacts everything in that model. That's why we call it a hyperparameter. So many models, many classifiers that we learn in this course have some hyperparameter that should be tuned. So here we are doing hyperparameter tuning for KNN using cross-validation. But this is only one use of cross-validation. There are many, many purposes. This is a very typical exam, typical use case. Other questions? Yeah. Oh, so K is the number of neighbors for KNN. Oh, come on. Well, it froze. The number of folds in practice is either 5 or 10. We either go with 5 or 10, that's it. Yeah, but K is the main question here. K is how many neighbors should I use for my classifier? For finding that, we try 1 and see how the classifier performs. How it performs is based on this and this. These are measures of performance where k is 1. That's why they have superscript 1. Yeah. If the length of the accessible data is not divisible by number of folds, the last fold can be a bit smaller. It doesn't matter. So ideally, they should be equal length, but sometimes the last fold is a bit smaller. Yeah, exactly. Yeah. So here, let me just recap from week 1. We also had this idea of a three-way split. You might be wondering why we are doing this complicated thing. So now I'm going to explain the motivation. The thing is, with a three-way split, we can also find the value of k, because it gives us a training set, a validation set, and a test set, and we can just train a KNN with k being equal to 1 and see how the error looks like. So the error is this much when k is equal to 1. Then we use k equal to 2, right? Train a classifier with k equal to 2, evaluated on this validation set, MSE is this much. So we can see that from here to here, the error, MSE is mean squared error, is decreasing. So it tells us that 2 is better than 1. And then we just continue this, and this is how we can use validation set approach. But one issue with validation set approach is that the result depends on the splits. The results depend on whether some challenging data point, which is also very informative, ended up in training or ended up in validation. So let's just consider that there is one data point which is really important for that boundary. If it ends up in training, it makes the model stronger, makes the model more capable. And then the validation, as that challenging data point is not in it, the evaluation is more lenient. But if the splits were different and that challenging data point ends up in the validation set, first of all, the model will not be as capable because it didn't see it in the training part, and then it is evaluated on it, so the evaluation is more stringent. That's why if you just use validation approach again, just with different split, for example, have the first part for test, this part for validation, this part for training, you get a different plot. That's why the validation set approach doesn't give you reliable measurements. I mean, there is some reproducibility here. For example, you can see that the general patterns of this data are almost the same. You have one substantial decline followed by some oscillation and tiny changes and almost stagnation. So in that sense, both of these plots are kind of telling us the same general story. But if you want to know what is the error of the model on something it has not seen before, in this repetition of the process, the error is like 24%. In this repetition is 10%. So which one is it? We don't know. We don't know because these splits also impact the measurements. That's why we don't mind doing something more complicated, which is cross-validation, because cross-validation is going to give us this plot. Cross-validation gives us a plot which is much more reliable, and if we repeat cross-validation, again we get the same plot, maybe with some tiny differences, but it would be impossible to get a totally different plot. So these data points, these circles, are means. For example, mean MSE cross-validated where k was 1 is this point here. And the standard deviation, I've shown it with these error bars. So I've shown one standard deviation, positive and negative error bars around it. Yeah. Yes, exactly. That's also okay. You can also use mean. I decided to give you a more sophisticated plot with more information. Later we will see what is the usage of these error bars. Exactly, because this is some U-shaped curve. You see that when we change k from 1 to 2, MSE decreases. MSE is error, so decreasing error is good. So between 1 and 2, we go with 2. But let's try 3. We try 3, and we also see that the error decreases. And this continues all the way to 4, but then from 4 to 5, we see the error increases. That's why 4 is the suitable value for the hyperparameter. 4 is the optimal value of k. Yeah. Tell this part of the story a bit later. So let me just first kind of explain the main things so that we don't worry about the variability. Then we move on to the technical details of what happens to these like error bars. Other questions? Yeah? Oh, yeah. Yeah. Yeah, always we prefer cross-validation over validation. Yeah, and implementing it is actually very easy. That's why I've never seen anyone using validation set. Yeah, but for us, validation set is something so that we understand cross-validation. Yep. No, this is for cross-validation. So this comes from here. So let me tell the story again from the beginning. So it was a bit complicated. So I hope you don't mind listening to it once again, because there are like different levels of understanding what is going on. This time I will also explain more details. So even if you fully understood the previous one, keep listening. So this is all the data we had. First, we separated the holdout data. We never used this for training or validation or any decision. This is for the last part of the project. The rest, we call it accessible data. This accessible data in black is also here. This is the same accessible data. I just created 3 parts, called them fold 1, fold 2, and fold 3. With these 3 folds, I can follow a kind of a systematic process to use them for training and validation, such that every single data point is used both for validation and training without having the same data point playing both of the roles for the same model. So this is like a 3-act play. In Act 1, fold 2 and fold 3 play the character of training. Fold 1 play the character of validation. For that model, this is just how the roles are decided. So no data point plays 2 different characters in the same act. But in the next act, you can see that now F1 plays role of training, F3 is also playing role of training, and F2 is playing role of validation. So this is a different model, and for this model, we have a different value of MSE. And then this whole thing is the aggregation of these values that matters. So we get 3 values of MSE. As there are 3 values, we can get their mean and we can get their standard deviation. So this is the mean, this is the standard deviation, and everything we did in here was for k being equal to 1. In the next step, we're going to try k being equal to 2 and follow everything. We do all of these and we get 2 other measurements. Yeah. No, it's not about accuracy being higher or lower. So we're doing this so that we get better measurements of performance of the model. Because the fundamental question is how good the model is going to do for data points it has not seen before. That's why we don't want to have any overlap between validation and training. At the same time, we want to ideally use accessible data, all of it, for training and for validation. So the systematic way of doing this, such that we both use all of this and we don't have any overlap, this is the systematic way. No connections at all. Number of folds, 5 or 10. K is the hyperparameter of KNN. And we could have been using cross-validation for polynomial regression. Then there is no K at all, but still we have some number of folds. So there is no connection. Yeah. 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 Short answer is yes, but the thing is, there are some theoretical results telling us that when we use 5 or 10, these are values that are kind of large enough that they shake up the data enough to make it random, and at the same time they are small enough that they don't create training sets which are highly correlated. So that's the other thing. In here, we want the model from this act of the play to be a different model from here. Because ideally, when you take the average of things that are far apart, you get a better result. That's why we want there's another sort of trade-off, which is number of folds. But we don't need to decide on that because some experts have done it, and the answer is 5 or 10. So we never need to worry about that part. That trade-off is deciding on the number of folds, which should be large enough so that it shakes up the data, and small enough so that these models would be different from one another. To be honest, no. This just happens to be some mathematical connection, but this is something else. But again, why we use 5-fold or 10-fold, it's really advanced. We don't need to really worry about it in this course. So just trust me, use one of these numbers. Yeah, the explanation is in your textbook if you're interested. But the short explanation is that 5 or 10 are not too small and are not too large. Other questions? And I also trust the authors of the textbook. So I just read the explanation a bit and said, oh, okay, this is enough for me. All right, so let's move to the code again. All right, so this is the same thing. This is all the data that we have. first we separate the holdout data, which is in orange, and the rest we call it accessible data. Then this accessible data here is split into 5 folds, right? We have these 5 folds. That's why now we have a 5-act play. We have a 5-step process. This row represents the first step of the process. In the first step of the process, we use fold 2, fold 3, fold 4, and 5 for training, and fold 1 for validation. In the second step, which is a different model, we train on fold 1, 3, 4, and 5, and validate on fold 2. That's a different model, different classifier. Then the next step, a new classifier, we train on 1, 2, 4, and 5, and validate on 3. And from each of these rows, from each of these classifiers, we get some MSE, we get some measure of performance. And then the 5 numbers we get from this process, we take their mean and their standard deviation. And that would be one point in that U-shaped curve that we want to trace out. Any questions? All right, so let's see how this works. So, all right, so for the iris data set, right? I'm going to first just import train test split just to separate out the holdout data. I select 30% of the data as holdout data and put it aside, yeah? And different classifiers, in all of them are KNN classifiers, but each of them is trained from scratch for that step of the process. So what I'm saying is, here we have one KNN, here we have a different KNN, which we trained from scratch. Here we have a third KNN. So in the sense that all of these are KNN classifiers, they belong to the same type, but they are different objects. It's not that we train something and we train it more in the next step. Each step we start from scratch. Yeah. Yeah. Yes, yes. Yeah. Yeah. Also, it's an object in the memory, right? It's a different object. Yeah. All right. So first, I separate out 30% of the data. That's this test data. Then for the rest, I call it y-accessible and x-accessible. So you may remember that KNN is a distance-based classifier. That's why the data must be normalized. So when I say normalized, this is confusing between different disciplines. By normalized, what I mean is subtracting the mean and dividing by standard deviation. So in statistics, normalization is something else, I believe. So just to give you an idea of what happens here, this is what I'm doing. If my data looks like this, if I have a feature with these values. Come on. So if I have a feature with 1, 3, 5, 7, and 9, autofocus. All right, so I have a feature in my data set, it's this. When I say normalized, what I mean is these numbers, I take their mean, the mean is 5, I take the standard deviation is 3.16. Then I convert this column to a different column, call it x norm, where I'm subtracting 5 from everything and dividing by 3.16. This new feature, what is special about it is that its mean is 0 and its standard deviation is 1. This is now a feature that is easier to kind of understand, because if in this new feature something is negative, negative means less than average. If something is, 4 or 5, it means it's 5 standard deviations above the average, right? So that's what I mean by normalization. I guess the more proper way of referring to it is saying using standard scalar from scikit-learn. But no one wants to be this precise. So this normalization must be done on the accessible data, not on the whole data set. If we normalize the data on the whole data set, or we do that before separating the holdout data, then our model suffers from data leakage, another fancy term. So there shouldn't be any overlap between training and validation, and definitely no overlap between training and testing. That's why we want to have this holdout data separated at the very beginning of the process. If we use all the data for normalization, the issue is that as the mean and standard deviation are impacted by every single value, then the test data kind of leaks into the training. Indirectly, it impacts the training. That's why the proper way of doing the normalization is doing it on accessible data. So here, you may remember this from the last session. So I'm using standard scalar from scikit-learn. This is exactly, it does what I had here. So I fit it to the accessible data, and then I transform the accessible data using that scalar. So what this does is exactly what I had written here, right? It just subtracts the mean and divides by standard deviation and makes a new column, which is x norm. Then I just set this normalized feature, I set it with the previous name. So now that the data is normalized, I can train I can evaluate my KNN model, KNN classifier, based on 5-fold cross-validation. And this gives me the mean training accuracy over the folds and the mean cross-validation accuracy over the folds. So for KNN, this thing is 1, which shouldn't surprise us. It overfits. But mean cross-validation accuracy is 0.94. What this means is that our estimate of how good the model makes predictions on things it has not seen before is 94%. Where does this 94% come from? It comes from here. There were 5 values, MSE1, MSE2, 3, 4, and 5. The algorithm took the average of them. The average was 94%. So 94% comes from 5 models. Those were the models in which some data were used for training and some for validation. That's why overall in all of them, all the data points, all the accessible data points were used for both training and validation, but in a systematic and smart way to avoid overlap. So here the cross-validation accuracy is 0.94. Yeah, this is for k being equal to 1. Now you might be wondering what would be the performance if k equals 2, right? So I'm training a different classifier with k being equal to 2, and you can see that training error decreases and cross-validation, this is accuracy. Training accuracy decreases, which is not a big deal for us because it was not a relevant measurement anyways. This is the relevant measurement, and we see that mean cross-validation accuracy has decreased from 0.94 to 0.92. When we try 3, it's again 94. When we try 4, it's 94. When we try 5, it's 96. Right? So you can see that so far 5 is the better option. When it's 6, again 96. Right? So between these values, we go with the value for the hyperparameter that gives us the highest mean cross-validation accuracy. That's the same thing as finding the minimum point of that U-shaped curve. Right? So, yeah. So this is now the part where we have decided on the hyperparameter. For example, we decided that the hyperparameter should be 7 because we noticed that over these values, I mean, the behavior was not monotone. This is because k is not continuous. That's why the behavior was a bit jumpy. But overall, it looks like a U, meaning that initially we get some improvements. Then after some point, it kind of, the error increases or the accuracy decreases, same thing, right? So we decided that k should be 7. Now what we're going to do is actually go back and train a new model with k being equal to 7 on all the accessible data. Because more data, more rows means more information for the model. So we don't want to be wasteful. We want to use all the accessible data for training. After we have decided on the value of the hyperparameter, we go back and train a 7 nearest neighbor classifier on all the accessible data. I want to explain this part a bit later because it's a bit more technical. Yeah. I haven't used the test set at all. So I just separated it and I've never used it. I haven't used it so far because this is not end of the project yet and it's not end of my story either. So we will use that at the very, very end of this Jupyter notebook. Yeah. All right, so let's say k equal to 8 was the best value, then we go back and retrain a KNN with k being equal to 8 on the whole accessible data. And oops, there was an issue. Let me just. All right. So here actually you can see that with 8 neighbors, the mean cross-validation accuracy is 94, but 94, let's say, was better than the other ones we had when we were tuning the hyperparameter. Here we decide that number of neighbors should be 8. Then we go back and retrain an 8th nearest neighbor classifier on the data, and then evaluate that on the test set. So this is the answer to your question. Here I have the test set. First, I'm applying the same scalar on the test set, and then I'm evaluating performance of the classifier and test it, and the performance is even better. Why is it better? Because this model is trained on all the accessible data. Yeah.